So for our next problem, what we have here is a beam that's projecting out 6 meters. So you can almost, and then there's a support beam that's pinned here at the wall and pinned here at the end. So you can almost imagine that this is like for a sign. And so what you see here, this distributed load, is the weight of the sign. So picture you have a sign and it actually it's getting bigger or heavier as it comes out. So it's 200 newtons per meter distributed load here, and it's then growing linearly up to 400 newtons per meter here in the end. All right. So this is shown pushing down, but it's the same thing as something hanging. It produces the same result. Whether I push here or I hang there, it's all the same. All right. So this is 2.5 meters. Here we have 6 meters coming out. All right. So first thing we need to do, well, let's just note for this problem, we're going to get the shear, the bending moment, the axial force at D, right here in the center of this beam. All right. First step in these problems, always, let's figure out the supports. But of course, before we do that, we got to do the free body diagram. So this, so compared to the last problem, this is a little bit more complicated of a distributed load. And what I'm going to do is I'm just going to break it up into two parts. So this was, it started at 200 and linearly grew up to 400. So I'm just going to break this down into a uniform load of 1200, of 200 newtons per meter over 6 meters. So that would, in the center of this uniform load, so this is just like just a box right here in the center, 200 newtons per meter over 6 meters would be 1200 newtons. All right. Then this part that went up linearly, so that's basically a triangle. So it starts from 0 now and goes up to 200. All right. So let's look at this. I've got 6 meters times 200 to be 1200, then times 1/2, because it's a triangle, says I have a 600 Newton force due to this part of the load. And since it's a triangle, what we learned from our center of mass work, that the center of a triangle, of a right triangle, is 1/3 from the fat end. So this is 6 meters, so I'll have 4, and there's 2. 1/3 of the way from the fat end. Okay? So here's 600 newtons, 2 meters off of this end. So there we have our load. So I can break this thing down into a 1200 Newton force dead in the center and a 600 Newton force 4 meters from this side, 2 meters from that. All right. Now, this is pinned to the wall here. So the pin can only exert forces in the X and Y. So if I look at this, it seems apparent that this support beam is going to provide a force going this way. So that has an X component out, so it looks to me obvious that, excuse me, AX needs to go back the other way. And with all the load coming in, this will be supporting it and AY will be supporting it. So those are my assumed directions. And here's FBC coming from here. This is a two-force member. We don't have any mass here, so the force will be between the connections or along the center line of the beam. And if we take a look at what this is, 2.5 and 6, we can just think of this as 5, 12. That makes the hypotenuse 13. So in terms of trigonometry, we have a 5, 12, 13 triangle. So that tells us everything we need to know. So now we can go after, given the free body diagram, we can go after the supports. All right, we're going to move this up a tad and pull this down. So going right here, if I sum the moments at A, I have 1200 newtons, that's 3 meters out. Here's 600, that's 4 meters out relative to A, plus FBC. The Y component will be the force here times 5/13, and then 6 meters out. All right, solving, I get FBC is 2600 newtons. Then summing in the X and the Y, from those, we'll wind up with AX is 2400 newtons, and AY is 800 newtons. So we've figured out all the supports. We're now ready to go and say, what's happening here at that center? All right, so we're going to move this over. And I'll adjust my focus here in a moment, or field of view. So there's the original problem. And so now here's the free body diagram associated with point D, which is in the center. All right. So for this free body diagram, what I'm doing is I'm keeping this half, I'm throwing away this half. All right. So if I do that, here is my 2400 pulling back AX. Here's AY coming up. I now only have 3 meters of the beam. The other 3 meters have been thrown away. And I'm replacing them by a shear. This shear goes down when I look at this half because it would take it clockwise. Bending moment coming up is trying to pinch the top, so I have that in the proper direction. And the axial force, I assume it's creating tension. Now, once again, once you see this force along the x, that force must be constant all along the axis. Therefore, N is 2400 newtons, and it's 2400 newtons everywhere. This is utterly, utterly boring. So we're not going to put it, this is actually the last problem we're going to even mention it. So if you just look at that, it's very apparent that N is 2400 newtons. It's intention. It's trivial. It's boring. I'm done with it. All right. Now, let's just take a look at what I did here. When you cut away the beam, all of that distributed load that's back here has been replaced, along with everything else, by this shear and this bending moment. All right. So, but this part of the original distributed load still remains. So now we have to treat this as its own distributed load and come up with the forces. So now over 3 meters, I have 200 newtons per meter. So that's 200 times 3, 600 dead in the center for this. So that's 1.5 meters over. Now I have, this is 100 newtons per meter because it went from 0 up to 200. It was linear. So it's 100 here times 3 is 300 times 1/2 for the triangle. So I have 150 newtons, 1/3 from the fat end, that's 1 meter over. And so there's my free body diagram. So given this, I can now go in some forces in the y very easily. I have 800 up, 600 down, 150 down. And so that's 750, here's 800. I dare say it's obvious that the shear is 50 newtons. All right, so don't need to write the equation. It's quite apparent. All right, so let's sum the moments. So we're going to sum the moments here at D. All right, so if I look at this, M is going counterclockwise, so I'll just put that in there. We have M. The axial lined up does nothing. I have 800 newtons, 3 meters away. That looks clockwise, so minus 800 times 3. This is 1.5 meters away. That's positive, counterclockwise. Here's 150. So I have plus 150 times 1. Okay. And solve for M. And we would come up with 1,350 Newton meters. So axially, and it's the same everywhere, 2,400 newtons. Shear here, 50 newtons. Bending moment, it's 1,350 Newton meters, and it is trying to pinch the top. All right, I will set up our next problem. We're going to kind of go all the way now. So we're going to set up a beam where we do these computations at every single point along the beam, and we generate a plot. So this will be our first problem where we're looking at the full meal deal. See you in a bit.